Let us now look at the 3-mark questions. Again here, a student is expected to answer only 5 questions. Question 1 says, obtain the relation between electric field and electric potential. Now this can be done in 2 ways. What is given in books, in most books, is like this, where there are 2 surfaces taken. Let us call this as a surface, say B, and also a surface A. So A and B are 2 equipotential surfaces, which means the potential on A is same and potential on B is same. That is, every point on A will have same potential and every point on B will have same potential, but the potential between point A and point T, that is, potentials on point A and B are not same. So let the potential at point A be some V, that is, on surface A is V. Suppose if we assume there is electric field present, electric field is always normal to a equipotential surface. So electric field will go out like this normally. So the field goes normally out of the surface. Let us take any one field. Let us call the electric field E. Let us take some point on this surface and some point on this surface. Let us move a charge Q. Now, if the potential on the surface A is V, then we know that, we learned in first chapter that if you have a point charge, say plus charge, say a charge capital Q, then if you look at a points, say point P1 and point P2, the electric field from the charge Q would go out like this because it is a positive charge. The electric field goes out radially from a positive charge. Between points P1 and points P2, the electric potential will decrease, which means the electric potential at point P2 is less than the electric potential at point P1. So in that sense, if you look at this, the electric potential on the surface V will be less than that on surface A. So let us call it as V minus dV. So the electric potential on any point on the surface B is V minus dV. Let the separation between the 2 surfaces be called as some dr. So dr is the separation between 2 surfaces. Let us assume that we move a small charge Q from a point on surface A to a point on surface B. Then the work done, the general formula is the work done to move a charge from initial point to final point is equal to the charge moved into V final minus V initial. This is a property. Using same property here, work done to move a charge from point A to point B, the charge moved is Q, that is equal to, it is the charge moved into potential at point B, because that is the final surface, minus electric potential at point A, which is VA. That is equal to Q into VB. The potential on the surface B is V minus dV, minus on surface A is V. It's all capital V's. So from here, V gets cancelled. Therefore, the work done to move a charge from point A to point B is minus of Q into dV. Let us call this as equation number 1. And also recall what is work done mechanically. Mechanically, the work done is equal to force into displacement. That's the work done. In this case, let us call it some work done W here. But this force in terms of charge would be F is equal to Q into E. And also here, the displacement dr and e are in same direction. Therefore, the angle theta here becomes 0. So, the work done to move from surface A to surface B would be F, which is Q into E into dr. Let's call this as 2. So, this is work done to move from point A to point B. Now, comparing equations 1 and 2, we can say minus Q into dV is equal to Q into E into dr. From this, Q gets cancelled. Therefore, what remains is E is minus of dV by dr. So, this is the required expression for a relationship between electric field and electric potential. This is one way of doing it. Or alternatively, what you can do is, other way is to recall the definitions of electric field and electric potential. Electric potential is given as Q by 4 pi epsilon naught into 1 by r, or we can write this simply as V is equal to K Q by r, where this K is equal to 1 by 4 pi epsilon naught. This is what is V, and also the electric field is given as K Q by r square for a single point charge Q. Now we can derive from here also. If we consider V is equal to K Q by r, if we differentiate this V with respect to x, that is differentiating V with respect to r, then what we get is, we get dV by dr is equal to d by dr of K Q by r. Now from here, for a given condition K and Q are constant, that comes out, so it becomes, that is KQ comes out, and what remains is d by dr of 1 by r, that is dV by dr is equal to KQ d by dr of r power minus 1. Recall that d by dx of x power n is n into x power n minus 1. Putting it back here, it is k into q, n here is minus 1, so minus 1, r power n is minus 1 because it is n minus 1, that is equal to k q with a minus sign, and this becomes r power minus 2 when it becomes r square. But this is nothing but, it is the electric field as seen earlier. Therefore, what we get from here is, we get dV by dr is minus E, or just bring minus this side, minus of dV by dr. So any one of this could be used to derive the relevant expression. #27 says, two resistors of resistances R1 and R2 are connected in series. Derive the expression for its equivalent resistance. So in this case, it's already given as R1 or R2 in series. Sometimes the question may tell you to just find the equivalent for some resistor, from some capacitors or resistors. If nothing is mentioned, it's up to student. They could take it 2 or 3. But the question says find for 2. Then find for 2 resistors only. So to solve it, let us consider a system where we have 2 resistors and a battery which is connected to it. Let us call this as supplying a voltage of V. So this battery would supply current I. Let the resistor here be called as R1. This is R2. In series combination, the current remains same, but the voltage will vary. So the voltage what I apply, it divides into 2 parts. A part of voltage comes across R1 and a part across R2. Let us call this as V1. Let us call this as V2. For example, if V is say 12 volt, then out of it, a part of it will come across R1 and a part across R2. That is, if we take a voltmeter and put across R1, it will measure voltage V1, and across R2, it will measure voltage V2. Now here, we need to find something called as equivalent resistance, which means that here we need to replace these resistor by a single resistor. That is, it is called as equivalent. Let us call it as R suffix S. So R suffix X here is the equivalent resistance, which means that this resistor will also draw same current for same voltage drop, which means in the previous case, if the voltage supplied by the battery is 12 volt or EMF is 12 volt and the current what came out of it is 3 ampere, in this case also for the same battery the same current would come out, which means from battery point of view, it doesn't matter whether it is 2 resistors or 3 resistors or any resistors. From battery point of view, whether you put this combination or single combination, the effect is same. The same current comes out. That resistor, that resistance is called as equivalent resistance. So we need to find what this RS is. So in examination, make sure that you draw this circuit also. So this also is very important to draw the equivalent circuit. In this case, the voltage drop whatever is applied, that breaks into 2 parts. So V is equal to sum of V1 plus V2. Let us call this as 1. But V itself from Ohm's law is given as I into R. So across the first resistor, V1 is equal to I into R1. That is because the same current flows through all the resistors, and V2 is I into R2. Putting it back here, in 1 what we get is we get V is equal to I into R1 plus I into R2. If we pull out I common from here, then V is equal to I into R1 plus R2. This is what is V. Let's call this as 2. Now similarly, in examination you write below this, don't draw line right here. I'm just writing it to explain it. Otherwise continue same sequence. Now say writing for equivalent circuit. Again using Ohm's law here, we get V is equal to I into RS. Let's call this as 3. But keep in mind that the voltage or the EMF is same. It's the same battery only. So if you compare 2 and 3, we can say from 2 and 3, write this in words also. In examination, don't just do it as mathematical steps, write some physical meanings also. That is, write these things comparing 2 and 3. Don't make the exam just mathematical equations, because it is a physics examination. So write these things also. So what you get is I into R1 plus R2 is I into RS. From here I gets cancelled. Therefore what we get is RS is equal to R1 plus R2. So this is a required expression. Again, if the question says draw for 3 or find out for 3 resistors, then you can extend same argument. In that case, RS is equal to R1 plus R2 plus R3. As a homework, you all can find out what is the equivalent resistance of 2 resistors in parallel. The answer would be 1 by RP is 1 by R1 plus 1 by R2. So practice this also. Even this becomes important. As I keep telling you all, that don't expect same thing will be asked examination. They may ask you something around this also. So in that sense, even parallel may become important. Practice this also. 28 says, using Ampere's circuital law, Obtain the expression for magnetic field at a point due to a straight, infinitely long, steady current carrying wire. Even this is quite important question. So let us draw a steady or a wire which is infinitely long, which means draw a wire of certain length and put at least 3 dots. This is sufficient, because if you put 3 dots, it means it is infinitely long. Let this carry current I. Suppose you want to find a magnetic field. The current here is steady current. You want to find a magnetic field at a given point here, at a point P. So at the point P, we need to find the magnetic field. For that case, we use Ampere's second law, which says that a line integral of B dot dl is equal to mu naught into I enclosed. This is called as Ampere's circuit law. Now, in such cases, whether using Gauss theorem or Ampere's law, what is very important is to find symmetry in the problem. Symmetry in the problem is very, very important. So you need to find that first. So in such cases, we need to find a Amperean loop, because in case of Gauss law, we have a Gaussian surface, and here we have Amperean loop. The simplest thing is to draw a circular loop around it, such that the loop passes across the point P. Since we need to find the magnetic field at the point P, make sure that the loop passes to the point P. That's the first step. Second step is we need to find a direction for the Ampere loop also. Let us take this direction as anti-clockwise. Here there are two directions taken. One direction is the current direction, which is already going from south to north, and there is a direction for the loop. Now loop direction is your choice, but if you take it to be this way, it becomes easy to solve it. In such case, what happens is, at every point on this, if we see from top, then what you would see is, you would see something of this kind. That is, from top, if you look at it, you will see something of this kind. So this is the Amperean loop taken, and then you just see a dot. This is the current carrying wire. This is what you would see. This is the top view. So in that case, the distance from this current loop to any point on the wire is same. So field at all points remains same. So in this case, B remains constant. So every point on this loop, B remains same. That's the first observation. Second thing is, we've taken the Amperean loop to be this way. So if we take a small element, in that case dl is tangent to it. So at this point, dl is tangential. So it will be like this. dl is tangential. Also, you learnt in theory class that for magnetic field, it will be tangential also. So at this point, even the magnetic field is in same direction. So at every point, if you take a small element, the length dl is tangential, and also the field is tangential. This arises only because symmetry in the problem. Instead of this, if you took some surface of this kind, then the whole thing will collapse. So Gaussian surface or Amperean circuit law is simplified if you have some symmetry in the problem. So with this in mind, if we look at this equation, the line integral of B into dl, it becomes into cos theta, because A dot B is equal to A into B into cos theta. That is equal to, here B comes out of the integral sign because B is a constant. For every point on this loop, B is constant. So B comes out, and also here theta is equal to 0 degrees. Theta is the angle between dl and B. Since theta is equal to 0 degrees, cos 0 is equal to 1. So even this becomes equal to 1. So what remains is, it is line integral of dl, which means we need to add all the small lengths. If the distance between the current carrying wire to this point P is r, which is nothing but the radius of this circle, which is taken as r, Then if you add all the small elements, that is dl means small lengths. If you add all the small lengths, what you get is the total length of the circle, which is its circumference. It is equal to b into 2 into pi into r. Therefore, what we got is, if you look at the Ampere law here, then b into 2 into pi into r is mu naught into I enclosed. What we want is the magnetic field. Therefore, the magnetic field is equal to mu naught I by 2 into pi into r. So this is the required expression for the magnetic field. 29 says, write any three properties of diamagnetic substances. Here I have compiled a table for all the materials, which is diamagnetic, paramagnetic and ferromagnetic. This is what is in the syllabus. There are much more beyond this. There is something called as ferrimagnetic, antiferromagnetic. It goes on. But for your syllabus, only three kinds of material is taken. So here I compiled all the differences. Learn any three differences. For example, you can learn, say, in case of diamagnet, it is repelled by an external magnetic field, which means if we have diamagnet material and if you have magnetic field like this, it will be pushed away, it will repel. While in case of paramagnet, the material will be pulled by the magnetic field but with a small attraction. In case of ferromagnet, it will be pulled towards the magnet with a strong force. So in case of diamagnet, it will be pushed away. So the magnet will be pushed away by this material. While in case of paramagnetic or ferromagnetic, the material will be pulled by the magnet, but the force will vary. Paramagnetic means it will be attracted with very small force, while if the material is ferromagnetic, it will be pulled towards the magnet by a strong force. So you can learn this as one difference. Second difference is mu r, which is called as relative permeability. That value is less than 1. So mu r is less than 1 for diamagnet. Mu r is slightly more than 1 for paramagnet. Well, mu r is very much more than 1 for ferromagnet, which means you observe that ferromagnetic case is something like paramagnet with stronger values. And one more example what you can learn, or one more point what could be learned is about psi. It is called as susceptibility. So psi is constant, small and negative for diamagnet, while for paramagnet psi is constant, small and positive. It is positive here. Then what should be for ferromagnet? As expected, psi should be large, positive, but it's variable here. So whatever you see as ferromagnet is nothing but strong case of paramagnet, but the behavior is very different. Just to understand, you can think that ferromagnet has properties of paramagnet with a stronger behavior. One more point which could be learned is its examples of it. So learn at least one example. Diamagnet, for example, like diamond, air, water. Paramagnetic, aluminum, sodium, and ferromagnetic, iron, cobalt, nickel. So just learn any this. Here what has been asked is only the properties of only one substance, but then if you compare and learn, you can remember in a better way, because sometimes the question could be asked to compare the three materials for one or two properties. So in this way this helps you all. There are many more properties given, there's no need to look into it. Just remember the basic three properties. 30 says, describe coil and magnet experiment to demonstrate the phenomenon of electromagnetic induction. To understand this, what is taken is, a diagram is drawn, but exam draw a diagram like this. There is a coil which is taken. I put the diagram just to get a feel of how things will be. We have a coil. The coil could have 1 turns or n number of turns, doesn't matter. We have a coil, and to this coil we have attached a galvanometer like this. Keep in mind that there is no source of power in this coil. We have only a coil to which we have attached a galvanometer like this. Now let us call this as coil, and then a bar magnet is kept close to it. Let us call as north and south. Whenever this bar magnet is moved towards the coil like this, then we know that a bar magnet will have its own magnetic fields. There was a question based on the magnetic field lines of bar magnet given earlier in the model paper. So the field lines will be like this. It comes out like this, it enters, and it is from south to north inside the magnet. This is how the field lines will look like. Now whenever the magnet is moved towards the coil, the flux in the coil will change. The magnetic flux, which is called as psi b, is defined as b dot a, or psi b is equal to b into a into cos theta. That is the magnetic flux. Whenever the coil is taken, or if the magnet is moved towards the coil, we'll take a case where the coil is fixed, only the bar magnet is moving. This is a bar magnet which is moving. What is seen is, as long as the magnet is moved towards the coil, current here is increasing. So once the magnet is stopped, current stops flowing here. So in this case, what happens is, if the magnet is moved towards the coil, the current in this coil will flow in anti-clockwise direction. So the galvanometer will show deflection in one direction. Say for example like this, it shows deflection in this direction. So more and more faster it moves, current will increase, and then current flows here. Suppose at some point the magnet is stopped, doesn't move, then current drops to 0. Suppose if the magnet is pulled away from the coil, then what is seen is, here the current would reverse direction. In the first case, the current was flowing in anti-clockwise direction. If the magnet is reversed, it is taken back, then the current will flow in clockwise direction. Current is reversed. So what is seen from here is, we can say, as long as there is relative motion between the coil and the magnet, current exists in the coil. But recall that current can exist only if we have an EMF. Without EMF, current can't exist, which means this moving magnet is creating a EMF in this coil. So as long as there is relative motion between the coil and magnet, an EMF is induced, and that induced EMF will give a current. Once the magnet is stopped, the current becomes 0. This is the principle here. As long as there is relative motion between the magnet and the coil, current persists in the coil. When the magnet stops, current becomes 0. When the magnet is pulled away from the coil, current still flows, but current flows in opposite direction. This is what you need to write here. Again, one more point which is required here is about something called as a Lenz's law, which I'll do in the next model paper. Otherwise it becomes lengthy here. 31 says, mention any 3 sources of energy loss in actual transformer. There are 4 kinds of losses. The question says just mention them. It doesn't say explain. Mention means just mention names of it. The first kind of loss is called as flux leakage loss. Second is eddy current. Third is Joule heating. Fourth is hysteresis loss. And what is given here is how to minimize it, because here there can be 2 questions. One question can be just to mention the losses as seen here, or they may ask you to mention the losses and how to correct them also. So flux leakage loss means, if you recall, say a transformer like this, sometimes what happens is there will be one coil which is wound around this and one wound around this. This is called as primary coil. Number of turns are NP. This is called secondary coil NS. So the flux will be lost here. Flux doesn't flow through this coil. So the flux has been lost like this based on the current direction. So the entire flux doesn't enter into this coil. That's called a flux leakage. Now how to avoid this? To avoid this, we can have the coils wound on each other, which means a primary coil is here, and on top of it, if we wind the secondary coils, then whatever flux is produced with primary, the whole thing will pass to secondary. So by winding on top of each other, we can minimize the flux leakage. Second thing is eddy current. Whenever a flux is changing here, there will be small amount of current flowing in this material. These localized current, it's like water flowing in a stream. If water flows in a stream, and suppose there's like a stone somewhere here, then what we see is you'll find the water will divert like this, but somewhere in some region there will be water circulating there only like this. It will not move anywhere. These are called eddy currents. Eddy currents is a general term. So don't think eddy currents is something which is used only in physics. It's a common term. Even the water motion is called eddy current. So in case of magnetic field, if we have material, then what happens is as long as flux is changing, here there will be localized electron motion. Electrons will move in small regions. That is called eddy currents. To avoid this, we need to cover it by some material that's called as laminating the core. Third thing is Joule's heat loss. Now, how much ever good conductor these wires are, there will be some amount of heat lost. Whether current flows in the primary coil or secondary coil, there will be some heat lost. It is called as Joule's heating. This can be overcome by using thick coils so that the heat loss is minimal. Fourth is hysteresis loss. Again, there's no need to understand because it's a big concept. Just learn the name, hysteresis loss, and this can be corrected by using something called as soft iron. Again, for this question, you just need to remember any three kinds of losses. Don't even write how to correct them. But the question is expanded and asked in different way, then learn this also. Because I've been telling you that learn even the associated questions also for each topic. 32 says, using Huygens principle, show that the angle of incidence is equal to angle of reflection. To understand this, we will take a mirror. We need to show that the angle of incidence is equal to angle of reflection by using Huygens principle, which is plane waves. Let us call this mirror ends as point P and point Q. Suppose, say, there is one parallel beam forming like this. Let us call this as, say, A. This is point B. This is point B. And let us call this as point C. This is point D. Now here, if you observe carefully, by the time the point B, the whole thing is a plane wavefront. So this whole part is a plane wavefront, which is called as incident wavefront. Now the angle made here is I. This is a normal. Now, since the point B hits the surface first, the point B will reflect. So the light from here will reflect and go like this. In the meantime, the point B goes somewhere, light from point D would hit the surface. Let us call this as point E. So by the time light from point B goes to point E, light from point B has gone somewhere else. So some point like this. After hitting the point E, light would reflect and go like this. So if you draw normal from here to here, this is called as this part. This part is called as reflected wavefront. So let us call this point as some point G. So by the time the light from point B goes to point G, or by the time the light from point D comes to point E, the light from point B has gone to point G. So the angle made here is R. And to find the distance, if the time taken by light to go from point D to point E is T, that's the time taken, then distance D into V would be speed into time, because speed is distance by time, or distance is speed into time. That is equal to, speed here is V into T. Some books will write C also, assuming the light is moving in air. So we'll call as V. There's no difference in what you write here. D into E is V into T. So the distance between point D to point E is V into T. Similarly, distance between point B to point G should be V into T only, the same distance. But to draw that, what you do is, from the point B, because if you want to mark a given distance, a more accurate way is to take a compass and mark an arc. So if we want to mark distance VT on this line, then what you can do is, from the point B we can take a compass of radius V into T. So if we draw it, then we get something of this kind. We get an arc like this. So the radius from point B to point G is V into T only. So even this is V into T. And the angle made here is 90 degrees. It's 90 degrees here. So this part, that is what I draw in black color, is the reflected wavefront. It goes like this. This is a reflected wavefront. So you need to prove this. I is equal to R. Now suppose the angle is I here, even this angle also becomes I. So this again a property of mathematics. This becomes I. Again, there is a reason beyond it. That is, if we push this line to fall along normal, that is, if we make AB to fall along the normal, which I call as N dash, then BG will be along BE. That is, if we press it, this line BG will come along BE. So angle moved by BG and then AB same as I only. Since AB moves away from N dash by angle I, BG moves away from B by angle I only. That is what is angle I here. And here also, look at this triangle. This is R. Just redraw this. Yeah, normal here is something of this kind. This is the point B. This is normal N dash. We have point here like this. This is point G. This is point E. Don't get confused with the ray BD. We are looking at BG. Here it is 90 degrees because it's a normal drawn here. This is 90 degrees here. This angle is R. This becomes 90 minus R because this is normal. N dash is normal. So normal makes an angle of 90 with the mirror, which is BE. This is 90. This becomes R. So this is what is one triangle. And also, if you look at one more triangle from here, if you look at triangle B, D, E, the angle made is 90 degrees because it's incident ray. This is 90. This is I. This is 90 degrees. Now from these two triangles, BG is V into T and DE is also V into T. From this triangle, let us find what is sine I. So sine of I is equal to VT, which is opposite side by the hypotenuse, which is B into E. Let us call this as 1. From here, let us find what is sine R. Sine R is equal to opposite side, which is BG, which is same as V into T, by the hypotenuse, which is BE, which is by BE. Let's call this as 2. So comparing 1 and 2, we can say sine I is equal to sine R, because the terms on right hand side are equal. This implies that I is equal to R. Hence, we have proved the laws of reflection. Here, other question could be asked to prove Snell's law for refraction. That will be done in the next model paper if time permits. 33 says, it's a very important question, 33rd one. It says, give de Broglie's explanation of Bohr's second postulate. To understand this, let us recall Bohr's second postulate, which says the electrons will exist only in those orbits in which the angular momentum is an integral multiple of h by 2 pi. This is called as Bohr's second postulate. When Bohr proposed it, it was just a postulate. It was not proved. But this was proved later by scientists called as de Broglie. So scientists called as de Broglie, G is silent here, de Broglie, he proved this. It took almost 20 years or more than 20 years to prove this. To understand this, if we look at an electron, de Broglie assumed that electrons are like waves. They are called as matter waves, which means anything in motion will have a wave associated with itself, and that wave is called as matter wave. That will have a wavelength which is called as lambda, that is given by h by p. A very important equation. Now since the electron exists around the nucleus, the electron will be in some orbit. So if electron is to exist in this orbit, the electron should be a form of a stationary wave. For example, think of a string in guitar, and suppose imagine that we plug somewhere, we make a disturbance here. In this case, what happens is, in the string we'll get a waves like this. These are called as standing waves. So even here also, the electron is present here as a standing wave, and distance between this to this would be its wavelength. So draw this also. Example, draw a circle and draw these loops, and distance between this to this would be its wavelength, called as lambda. Now the condition for it to exist, the electron can exist in the orbit provided the distance available is a multiple of lambda. That is, for example, if you look at the string of length as 2 meter, then the wavelength can exist such that the wavelength should be a multiple of this, or the length of this should be n times lambda. For example, if we have wavelength of half a meter, then here we'll have 4 waves. That is what n is. If you have wavelength of say 1 meter, there are 2 waves here. So we can say that the length available should contains n times wavelength. Use the same idea here. The length available in this case is its circumference, which is 2 into pi into, we'll call a general case where it is Rn. It's the nth radius. So 2 pi into Rn is equal to n times lambda. This is a equation for a condition for standing waves, where 2 pi Rn is n into lambda. But if you look at matter waves expression, then from here 2 pi into Rn is n into lambda h by p. But p itself is linear momentum, where p is equal to mass into velocity. Let us take an nth orbit where the electron has velocity of Vn. It's the nth orbit. So we're putting suffix n here. So in this case, p becomes m into Vn, just the nth orbit. So 2 into pi into Rn is nh by m into Vn. From here we will rearrange the terms. So what we get is m into V into Rn, that is m into Vn into Rn. It's nh by 2 pi, but this itself is the angular momentum in the nth orbit as given here, because L is given as m into V into R. This is angular momentum, therefore L is equal to nh by 2 pi. This is the required proof. 35 says, write any three differences between nuclear fission and nuclear fusion. So in any question, when it comes to differences, the first and foremost is to write its definition. So it's a process. You can write a simple language saying that nuclear fusion is a process in which heavy nuclei splits into two lighter fragments, giving out energy. If you have big nuclei, that breaks, giving out small fragments plus energy. That is called nuclear fission. Nuclear fusion means, it says fuse, it's a common English word. In that case, what happens is two small nuclei will combine to give a bigger nuclei and also giving energy. That's called as nuclear fusion. Just write in simple language. Second difference is fission can take place at all temperatures, while fusion, for example like seen in sun, takes place only at high temperature. That's the second difference. Third difference is nuclear fission can be controlled. This can't be controlled. Fourth difference is, learn any three differences. Fourth one is, the energy per unit mass is less. Its per unit mass is less. Here energy per unit mass is more than nuclear fission. That's the differences. 35 says, explain the action of a Zener diode as a voltage regulator. Here keep in mind that for a Zener diode, it operates in reverse bias voltage such that if the current is for a given range, it will not still be destroyed. That is, for a normal diode, if we draw its IV characteristics, if you look at reverse bias condition, when the current crosses a given value, it will be destroyed. So if we cross this value of the voltage, it will be destroyed. But this Zener diode is a special kind of a diode, which means it operates only, or it operates better in this breakdown voltage. So this diode has a range of current for which it will not be destroyed. For example, it will have minimum and maximum value. This is called as IZ minimum and IZ maximum. For example, imagine that it can take up to 50 microampere current, which means even the current goes up to 50 microampere in reverse bias, still it will not be destroyed. This is what is IZ maximum. Just think of this number. Now here learn the circuit diagram. It has a power supply. You can just draw a straight line like this, that's sufficient. It has a power supply, a straight line like this, and then we have a resistance called as RS. This resistance is connected so that even if the load resistance becomes 0, the diode is not destroyed. Otherwise, suppose if the load becomes 0, then all the current may flow through this, where it may destroy the current, destroy the diode. Keep in mind that diode can take up to certain value only. Even though it operates in reverse bias condition, the diode can take only up to certain value, not beyond that. Now here observe carefully that the diode is in reverse bias condition because this is P region, this is the N region. So positive going to N type is called as reverse bias. Now here load means something which can draw power. Example, think like a fan or refrigerator, something which draws power is called as a load. Let the output across this be called as V0. Now ideally what we want is, we want that the output V0 is always uniform, it should not fluctuate, it should not change. Suppose if a current I comes out of this power supply, then the current at this point finds two branches. A part of this current which is IZ goes here and a part of current which is IL goes here. So when the current IZ passes through this diode, it will have a constant voltage seen here. Whether current is somewhere here or here, doesn't matter, voltage is constant. So this is what is the voltage, we call it say V some naught or say Vz. So this is the Zener voltage. For example, think it's like some value. Now what happens here is, since the load and the diode are in parallel combination, the voltage drop across this is what appears here because it's in parallel combination. So we need to keep this to be constant. To understand this, we'll take a case where suppose Vs increases, that is the power supply coming home suddenly increases. Then what happens is, if Vs increases, current also will increase. Suppose imagine I earlier was say, for example, it's like 2 ampere, or we'll make it less, we'll make it say 500 microampere for example, out of which the current flowing here is say 25 microampere. Remaining current flowing here is 475 microampere. Suppose if I increases, the current what you want across load should be only 475 microampere, not beyond this. Now suppose current increases, I becomes from 500, say I becomes say 520 microampere, current is increased. The current increases, what happens is current may increase here also, but what we want here is only this is what we want, not more than this. So an extra current of 20 microampere is entering the circuit. But if in that 20 microampere, if a small part goes to this, it will keep V0 not constant but vary it. But keep in mind that the diode can take up to 50 microampere current, which means the extra 20 microampere goes into the diode only. It was early 25 microampere plus now extra 20 goes into this only. So the current now flowing is 45 microampere. It can take up to 50 microampere. So whatever extra current is coming, extra current is flowing through the diode only, such that the output here remains constant, which means even here it remains a constant. This is one case of it. We'll take a second case where suppose Vs is constant, that is the supply voltage is constant, and this RL say decreases. By some reason the load doesn't decreases. Now even this would ensure that current increase in circuit. So in such case also, even if RL is decreasing, current will increase. In the first case, RL is constant, the power supply voltage only increased, because of which current increased. In this case, the power supply voltage is constant, but the load is decreasing. If the load decreases, current will increase. Again here, same as the previous case, the extra current whatever is not required will flow through the diode. So this diode can absorb extra current, or this diode can give some current out of it also. In all the cases, whether current increases or decreases in the diode, the voltage across it remains constant. because of which the voltage across the load remains constant. Though this behavior of a diode where the voltage across the load remains constant is called as voltage regulator. So in exam, you should draw this diagram and explain these 2 points. Again, here there's no need to put numbers in examination, just write in common words telling that if the current I increases, the extra current may destroy the load, and because of which the extra current flows to the diode. Same explain the second point also.